In this video, we are going to be looking at starting to do some inference with our regression equations. And so basically what we have learned so far has just been the ins and outs of how to find a regression equation and some information that goes along with that. Now what we want to start doing is using the fact that this regression equation has come from a sample to try to make an inference about the whole population. So when we were working through some of these problems where we were finding linear regression equations, we had this example of a grocery store that had surveyed 20 random customers, and they'd observed the number of items they'd purchased and found out how many days it had been since they'd last been there, and had come up with this regression equation that the number of groceries that they buy is going to equal 4.21 times the number of days it's been since their last visit to the store plus 3.27. Now, if we were to select a different group of 20 customers, would you expect this regression equation to be the exact same thing? Well, you probably said no, and that would make sense because if we take a different group of 20 customers, there's going to be some variability in their answers. And so we might expect it to be something similar to it, but it's probably going to be slightly different. And so that comes from the fact that we're looking at a sample instead of looking at the entire population. So what we want to do is to take the information that we got from the sample, take this value, for example, 4.21 that came from the sample, and start to do like we've done several times this year, which is to make a confidence interval based on that value. So as we go through this, our confidence interval, our point estimate, is our slope. Okay, that's the thing that's the piece of information that we're going to kind of focus on today, is that we've gotten this point estimate from our sample, and we're going to try to extend that out to the population. So on the back of your formula sheet, you have some formulas where it talks about the sampling distributions for simple linear regression. And it talks about how your variable is the slope. That's what we're looking at today. Okay, then for the population slope, our estimate would be the same as what our slope is, our point estimate. But then the spread of that would be, so in other words, if we went out and did this same survey multiple times, we're not always going to get 4.21 for the slope. It might be 4.21 one time, it might be 5.7 one time, it might be 3.8 sometime. So how are those values spread out? And that's based on this standard deviation, the standard error that we would calculate. And so if you notice, we've got three formulas there. It's really the top formula that tells us the standard error for the slopes, but we're going to substitute in a value S that's based on this equation, which if you notice, that's really just our residual values divided by n minus 2 and the square root of that. And then for Sx, that's really the standard deviation of our x values, but notice it gets multiplied by the square root of n minus 1. So it's kind of a strange formula. And so this is a pretty complex thing to actually come up with as far as the standard error for the slope. And so before we can really spend a whole lot of time with that, though, we want to make sure that we can actually come up with an inference based on our sample, because again, our inferences are only going to be as good as our samples are. So we want to make sure our samples meet the following requirements. First of all, we want to make sure that if we're going to do a prediction of the slope of a population regression equation, that our original equation is linear. Okay, that would make sense. The relationship must have a linear trend. And so if we look at kind of our first scatter plot here, we talked about this early on in section 8.1. If we look at that residual plot and we see some kind of a pattern, that tells us that a line is not a good way to fit that equation. And so if this was what our residual plot looked like to start with, we would not want to do this process that we're talking about. Something else you want to make sure is that the residuals are fairly normally distributed. In other words, we have a lot of them kind of in the middle and a few on either ends. So we want to make sure that we don't have like excessive skew, or we don't have outliers in that. So here's an example where we would have that. Okay, notice most of these residuals are pretty close to the center, but we have one that's really an outlier. We've got one that's way down here from our data point. So we've got some outliers going on there. So that would also be a case where we would not want to do this inference we're going to talk about. We want the variability to be consistent for all values of x. So this is what we mean by that. If you look at this linear regression line, notice that down here on the left side, we don't have a whole lot of variance in our values. They're pretty close to the line. But as x gets bigger and bigger and bigger, it kind of cones out. And towards this end, we have a lot more variability. So depending on the value of x, the amount of variance that we have in our answers increases. And so this would be another case where we would not really want to make this inference for our regression equation. And the last thing we want to make sure is that the observations are actually independent. In other words, one value shouldn't influence the next value. And so here's an example where we might have that going on, because if you notice, as we start to go below the line, everything's below the line. And then we go above the line, everything's above the line. And then we go back below and everything's below the line. And so one of the places where this happens is when we do a time-based observation, because usually if something is positive at 1 second, at 2 seconds, it's probably still going to be positive. And at 3 seconds, it's still going to be positive. And so one data point influences the next data point. And so we want to also watch out for that when we're making these inferences. So basically, just to kind of summarize what we need for the data to be coming from a random sample. We've always said that. And then we want the residual plots to just kind of appear like a cloud of points. We don't want to have a pattern. We don't want to have outliers. We want to make sure that it's kind of constantly distributed. Those are the things we want to look for in that residual plot. If those conditions are met, then the confidence interval is going to be the same thing we've always done. It's going to be a point estimate plus or minus a critical value times a standard error. And so the point estimate is going to be our slope that we've calculated before using this equation. The critical value is going to be a t-score with n-2 degrees of freedom. So if we have 20 samples, we would use 18 degrees of freedom when we would look it up on our t-chart like we've done before. And then the standard error is going to be given by that equation that we just talked about before. Now notice when you're finding this value, this s in this equation is not the standard deviation of the y like it was with our correlation or with our slope equation. Okay, it's just S. It's just a standard deviation of the residual values, in fact. And so you also notice that standard deviation, that S gets divided by the square root of n-2 instead of the square root of n-1. And so we've got some strange things going on there. So normally what we're going to do to get these values is we're going to use some kind of statistical software, which is why the last video spent some time looking at how to use Google Sheets. So I'm not expecting you to actually find these values using a formula. I'm expecting you to take this information, plug it into a Google Sheet, and then find it from there. So let's go through an example. We've talked about this grocery store problem, so we'll just spend a little more time with that. So basically, we've taken the data. I don't have the data here in front of us, but if you want to go back in your note packet, you can see the data that we used for this grocery store. And I've plugged it into Google Sheets, and this is the information we got out. That for the slope, there's our coefficient, there's our standard error. Same thing with the y-intercept. Got a value for r squared. And then we got the value from S. And so those are the first 6 boxes that we talked about there on Google Sheets. So the first thing we want to make our 95% confidence interval here, first thing we want to do is find the point estimate. So if we're going to try and find a confidence interval for the slope, which one of these numbers up here would be our point estimate? Okay, it's going to be the slope. And so this 4.209, or I've rounded here 4.210. What is the standard error that's associated with that point estimate? Since we're talking about the slope, it's going to be the standard error of the slope, and so it's going to be that 0.778. Okay, now in this particular problem, how many degrees of freedom will we have? Well, there's 20 customers that we've surveyed, so degrees of freedom is 20 minus 2, and so we would have 18 degrees of freedom. Now we want to come up with our critical value. So you want to pull out your T formula sheet, which I think I may have put a link to that on your assignment when you get ready to do your assignment if you don't have one handy. But on that T sheet, on your T distribution sheet, we want to look at the row that has 18 degrees of freedom and then go over to the column for 95%. Remember, that's got 0.025 up at the top of it. We want to find that T star value. So what would the T star value be at that point on your chart? Okay, when you looked it up, you should have found a T-star value of 2.101. So now we've got all the pieces we need. We just need to assemble that together as a confidence interval. So again, it's going to be the point estimate plus or minus the T-star, the critical value, times the standard error. So that's going to look like this. It's going to be 4.210, point estimate, plus or minus T-star, 2.101, times the standard error, 0.778. So we're going to subtract that, get a low value, add it, and get a high value. Okay, so which one of these is your confidence interval when we do that? Okay, so what you should have found is when you take 4.210 and add, you get 5.837. When you subtract, you get 2.567. So what we're saying is that we are 95% confident that the regression line for the entire population is going to have a slope between 2.567 and 5.837. Now, as your notes say, don't forget that that slope is actually telling you the average amount that y will change for a change of 1 unit next. So another way that we can kind of make a conclusion about this is we could say that we're 95% confident for each day it's been since a shopper's been to the store. Remember, that's our x values. They're going to buy between 2.567 and 5.837 more items. I don't know why I left more items off of that phrase there, but that's what's going on is that slope is telling us that if we increase x, if we increase the number of days by 1, this is how much y, or the number of items, will increase for each one of those days. Now notice that our slope did not include 0. Okay, both of these numbers are positive. So we're saying that we know that this line, or we are 95% confident anyway, that this line is going to have a positive slope. So since we're saying that we're 95% confident that that line has a positive slope, since that entire interval is greater than 0, we can also conclude that we are 95% certain that there's going to be a positive correlation between the number of days since the shopper's been to the store and the number of items that they purchase. And so that's another conclusion that we can make because 0 wasn't in that interval. If 0 was in that interval, we wouldn't be able to make that conclusion. All right, so that's what you're going to be working on today, is finding some of these confidence intervals for slope. So again, use Google Sheets to find all your information, and then just do a little calculation with your point estimate, with your t-star that you'll look up off your distribution table, and the standard error, again, that you'll get from Google Sheets. Use that to find out what your confidence interval is. If you have any questions, make sure you reach out to me with my email or with Canvas Messenger, and I will try to get back with you as soon as I can. So good luck with that. And as we kind of close today, here's some more kind of a statistics cartoon here about different types of regression equations. And so I'll just leave that with you as we close today.